Hi, this third particle in a box lecture is something of a sweep up, but it's like sort of a conceptual discussion of what we've gotten. In the previous two lectures, it got sort of mathematically technical. There were a lot of boundary conditions, decisions made, and choices. Like, you had to make decisions, and your decisions were informed by making sort of physical arguments. It might be instructive to actually go and rewatch the second video and try to understand all of the decisions that I made as I was deriving the solution to the particle in a box. But you might wonder, okay, so if he didn't make the particular decision he did, what other decisions could he have made? And what would be the implications of those choices? Are those choices physical? That is, do I get something that makes some sort of physical sense in light of how I know how to measure probabilities and, say the statistical statements that you can say with quantum mechanics? Or do those other choices give you absurdities, give you non-physical, non-possible situations, right? And honestly, that's more of what physicists do. Physicists don't jump in blind and just do stuff. Physicists are always motivated by, first of all, a physical system that they want to model. Maybe they have some properties that they really want their physical system to exhibit. So they're trying to look for underlying physics that would give them the properties that they want. Right? So motivations of physicists aren't just to like have a math problem and solve it. Yeah, but anyways, let's study the answers we got for the particle in a box. So our wave functions, they are indexed by a quantum number n. So right there, quantum number n, and n we found was restricted to have values from 1, 2, 3, up to infinity. We had energies, which were dependent on the quantum number n squared, pi squared, h bar squared, over twice the mass of the particle times the length of the interval squared. And we had wave functions that were essentially piecewise defined, but let me just point out in the earlier videos we had this region 2 piece of the wave function. They were indexed by n, and equal to square root 2 over L. That was the normalization factor. And on our interval from 0 to L, could only have these wave functions, where the only meaningful place that the quantum number shows up is in the k value, which you can talk about as a wave number, but the case of n were n pi over L. Let me make sure. Yes, that's right. So yeah, the wave functions are indexed like that. So this was only true, remember, on the interval from 0 to L. Okay, so here's some basics. So this is a bit of a terminology or a vocabulary word. So the ground state is the name reserved for the quantum state of lowest energy. So the ground state energy, in our case, is n equals to 1. So the ground state energy is pi squared h bar squared. Right? And the first excited state is actually not n equals to 1, it's n equals to 2. It's the first energy above the ground state. And the second excited state is the third energy above the ground state. Like that. So it's a matter of naming. But these are the states, or I mean, these are the energies of those states, and the quantum state itself is described by the wave function. So this would be that n equals to 1. So the quantum state of lowest energy is this wave function. The first excited state is described by this wave function, and the second excited state is described by that wave function. Okay, so these energy levels are sometimes referred to as the energy level spectrum, but this is somewhat misleading. So these E sub n, right? It's n squared pi squared h bar squared 2ml squared underneath. Sometimes this is referred to as the energy spectrum, but I don't like this because it implies, right? So what does spectrum imply? Spectrum is the light that we see come from our quantum system. The light actually isn't part of the quantum system, but the light is the way our system switches quantum states. So here is a possible transition. So a transition from, let's say, the third excited state to the ground. Remember how the excited states are counted? The first excited is actually the second level. The second excited is the third level. So the third excited state is the fourth level, and the ground is the first or the bottom level, right? The n equals to 1. That's the lowest quantum number that's possible. Remember, we don't allow 0 or negative values. So we're going from the third excited to the ground state, and there is a difference in the energy that comes from a transition from 4 down to 1. And it's equal to the fourth level energy minus the first level energy. And I'm going to, actually, I don't really like my language right now. I'm going to say that the energy associated with a transition from our quantum system being in level 4 down to level 1 is all taken or taken away from the system in the form of a single photon, and the energy of this single photon, which you know is h times f, is equal to the difference in the energies of that system. And this is just the conservation of energy. We used to have a bunch of energy stored up in our quantum system, and a little bit later in time, we know our quantum system has less energy. So where did that energy go? Well, it didn't disappear from the universe. It became something else. And that's one of the ways to understand what photons are for, right? So photons take away the extra energy. And when we think about the spectrum, we really think about the light that comes from the quantum system. And this right here is an energy in the spectrum. The fourth level energy and the first level energy, we actually never see those individually in the spectrum. In the spectrum, we only see all of the differences, right? You'll remember this. This is the way that we talked about Bohr model levels and the various, like the Balmer or the Passion series from the Bohr model. But anyways, yeah, so I think this is an important conceptual point to bring up, that we can study this very simple toy model of basically an unrealistic quantum mechanics problem, and nonetheless, it gives us an energy level difference spectrum. Okay, so the last thing I want to do here is just simply draw a picture of the psi sub n. So remember that the psi sub n all have the same first coefficient. And that's actually kind of an interesting thing, that the normalization constant, or the normalization factor, is independent of the quantum level. Usually it's not the case. Usually the normalization factor depends on the quantum level somehow. So you'll see an n inside in some squared or natural log or whatever. But anyways, in this particular case, it's not dependent. And then we get these sine n pi over L. Those are the k sub n's times x, right? And this is only true for x values between 0 and L. And the psi sub n are actually 0 outside the interval, right? Okay, so what do these functions have to look like? Well, let's look at them. So let's look at psi sub 1. Here's the x-axis, and the vertical axis I'm going to draw as psi of x. So I'm just drawing the first wave function. So let's change the color to black. So it's 0 outside the interval and has this interesting value on the inside. So, so 0 everywhere and 0 everywhere on the other side of L, right? And in between, it's root 2 over L sine 2 pi over Lx. So in n equals to 1's case, it actually looks like this. So let's draw psi sub 2. Let me change our drawing implement. So psi sub 2 actually is really similar in the forbidden zones, but psi sub 2 is interestingly different. If you go through the motions, you go and you put a 2 in for n right here, you'll get 2 pi x over L, and that means that as x varies from 0 to L, because you have this factor of 2, the argument varies in a sense twice as much, which means in the same interval, I can get the sine wave to vary over what looks like one full wavelength. Whereas with n equals to 1, because I only had a factor of 1 in here, when x varied from 0 to L, the argument, because there was only a 1 here, the argument varied over a sort of only over the half interval, or the 0 to pi variation. Let's continue. Let's do psi sub 3. So psi sub 3 0 up to the end, 0 after the other end, and in between looks like this, right? So what you're seeing is lambda 3 is smaller than lambda 2. Right? Isn't that what that looks like? The wavelength looks a little smaller as the index n gets bigger and bigger. But you also know that the energy of 3 is bigger than the energy of 2. Right? So as the wavelength shrinks, we're watching the energy grow. But also remember that de Broglie says that the momentum is this h over lambda. And the energy is like p squared, right? So the energy goes like p squared over 2m. That's the kinetic energy. Remember, in the interval, the potential energy is equal to 0. So the energy is just the kinetic energy. And you can kind of see that as the wavelength shrinks, right, the energy is growing, but the energy is growing because the momentum is inversely related to the wavelength. Like, all of these things are working out. And quite honestly, this is why Schrodinger knew his equation was important. Is it was doing the right thing. It was quantizing energy. It was having a sense of wavelength. Um, it was ultimately shown to give you all kinds of Heisenberg uncertainty principle stuff from its wave functions, right? Which you interpret with probability. Yeah. Let me point out that I want to say one last thing in this lecture. It's got to do with something that I see books do, and I wish they never did it. Here, I'm going to draw something that is found in books or on the internet when you search around. What they do is they actually draw the potential. So you know that U goes to infinity. And then they draw, here is the x equals to 0 location, the x equals to L location. And then they connect through here. So they drew the potential. And then inside, they go and draw the wave functions, but they draw them at different locations. So they draw the first wave function looks like this. The second wave function looks like that. And the third wave function, oops, let me do this better so it goes, oops. Like that. And they say this is the n equals to 3, n equals to 1, n equals to 0. And they are trying to imply that somehow the particle lives higher up, right? This is misleading because the truth is these shapes are not on an axis of energy. They're on an axis of square root of probability. So really, can you see that all of these axes, right? They're meant to the height of them. If you think about it, right, the maximum value of psi sub 1 is going to be the square root of 2 over L. And the units of this is definitely not energy, right? So the height of the function, right, the up-down meaning of the function, the wave function, it's not energy. But it kind of looks like that's what they're implying in this drawing. This drawing, they're just trying to show you how the wave function fits within the boundaries. But the up-down, there's actually two axes going on. There's energies implied when you talk about these things, these infinities, but it's also sort of mixing in wave function as the vertical axis. That's why I think that's misleading. I think it's better to sort of draw them all on their own axes, because really they're all separate issues. Okay, that's cantankerous, but yeah, I said it.